Welcome to this mega presentation on power quality and motors. Motors are one of the most common tools used in industry today. They're used in virtually all aspects of industry. Poor power quality can have adverse effects on motors and lead to premature and sudden failures. These failures can cause unscheduled downtime with significant loss in production. In this presentation, we'll cover some power quality phenomena and their impacts on motors. So, what are some common motor failures? Bearing failures are arguably the most common type of motor failures. Bearing failures are often blamed on poor lubrication. However, there are other causes of bearing failures, and these can be mechanical issues or their root cause can be due to power quality phenomena. Mechanical issues such as misalignment, faulty motor mounting, contamination, or poor sealing can cause bearing failures. Other issues that can lead to premature bearing failures include vibration, as well as electric current passing through the bearing, creating arcing. Faulty bearings can cause vibration. However, the opposite is also true. Vibration can lead to faulty bearings. Now, the root cause of vibration can be a mechanical imbalance, such as a misalignment. However, also negative sequence harmonics can also lead to vibrations. Negative sequence harmonics are harmonics that have magnetic fields that rotate in the opposite direction of the rotor's magnetic field. The negative sequence components can produce a resultant field or vector field. The direction of this field will be determined by the relative strength of all the magnetic fields, and this can lead to motor vibrations. Negative sequence harmonics are a byproduct of 6-pulse converters, which are commonly found in 3-phase power supplies, and these are often used in variable frequency drives or VFDs. Now, a certain level of negative sequence harmonics is always present in motors as a result of the stator field quantization as well as rectification. It is in the presence of the harmonics at higher levels that increases heating effects as well as the likelihood of capacitive coupling, resulting in bearing discharge and fluting failures. Another cause of bearing failures is excessive shaft current. Now, all motors have a certain amount of shaft voltage. Generally, shaft voltage should be less than 0.5 volts. When shaft voltage increases, it can lead to arcing between the bearings and the raceway, causing pitting, which will lead to fluting of the bearings. This can create motor vibration as well as audible noise, resulting in motor failure. When the motor shaft is turning, the bearing grease acts as an insulator. It insulates the bearings from the bearing race. The grease acts as a capacitor. The stator and the rotor generate charge through capacitive coupling. This is electrostatically induced into the motor shaft. This current then passes through the motor shaft to the bearings. If the difference in potential is great enough, it will create a discharge arc between the bearing and the race. This discharge is what causes bearing pitting. VFDs convert AC to DC. Insulated gate bipolar transistors, or IGBTs, are used to convert the DC back to a variable frequency AC control. IGBTs have fast switching times. This reduces energy losses, allowing for higher efficiency. However, these fast switching times create parasitic capacitance between the motor stator and rotor. Winding failures are another common cause of failure, and these can occur due to overheating and/or shorts between coils. Motor heating can occur due to several different power quality phenomena. Motors are constant power devices. As the voltage goes down, the current goes up in order to maintain the power. The heating is a function of current squared times the resistance. As the current rises, the heat rises exponentially. Unbalance. Just a 1% unbalance in the phase voltage can lead to a 6 to 10% unbalance in phase current. This current unbalance will generate unbalanced heating effects in the coils. This leads to uneven phase heating. Depending on the winding configuration, Y or delta, a phase or two, respectively, will be heated more than the others. This can lead to failure of these coils. Harmonics create eddy currents in wires. These eddy currents create magnetic fields of their own that push the current going through the wire to the outside edge of the wire. This is known as skin effect. This increases the heating effects in the wire. In addition to skin effect, coils have wires that are adjacent to each other. Adjacent wires create magnetic fields that push the current in the adjacent wire to the outer edge, and that's what's known as proximity effect. This further increases motor heating effects. The higher the frequency of the harmonic, the greater the heating effects. Transients can be another cause of winding failures. Transients create high instantaneous differences in voltage potential, and this can lead to arcing, and arcing through insulation will carbonize the insulation. This will lead to insulation failure, leading to shorted coils. High-speed switching, such as from VFDs, can create overshooting. As wire length or switching speeds increase, the overshooting peak voltages will also increase. Now, variable frequency drives create high-frequency pulses or voltage waves. Voltage wave reflection occurs when the impedance on the other end of the cable run does not match the impedance on the other end. This causes the voltage pulses to be reflected back in the direction from which it arrived. As these reflected waves encounter incoming waves, these values can add, causing higher peak voltages. These transients can be magnified due to the added capacitance and resulting wave reflection of long cable runs. When these pulses exceed the maximum voltage rating of the motor, they can cause insulation breakdown. And this is one way in which long cable runs can cause motor problems. Resonant conditions are created when the inductive and capacitive reactance becomes equal in an electrical system. Resonance in a power system may be classified as series or parallel resonance, depending on the configuration of the resonance circuit. Parallel resonance can lead to high currents through the cap banks. In a harmonic-rich environment, both types of resonance are present. In this example, if we calculate the resonant frequency, we can see it's about 159 hertz. At this frequency, the impedance of the capacitance and the inductance are the same, about 100 ohms. If we remove the resistance portion of this equation, we can see that the impedance of this parallel circuit approaches infinity as the denominator approaches zero. The energy stored in the magnetic field in the inductor now collapses and runs through the cap, and the energy in the cap flows through the inductor, creating a high circulating current. At the resonant frequency, impedance is at a maximum, and high amounts of harmonic voltage appear because of the circulation of the harmonic currents. This results in major voltage distortion, as well as a high circulating current that can lead to catastrophic failures. Current inrush testing is another common test that is performed on motors. When a motor is energized, a large inrush current will be seen until the motor gets up to speed. Inrush testing allows for proper sizing of protection equipment, and it also verifies the motor is not exceeding its limits. Now, in order to adequately view inrush data, you need to be able to view the data over multiple cycles until the inrush is stable. In order to do this, a waveform of at least 10 seconds should be captured. And for very large motors, it may be needed to capture waveforms for up to 1 minute. To perform inrush testing, it is recommended to record both RMS data as well as waveform data. And that RMS data should be recorded every cycle. A waveform capture will be triggered using a current swell trigger that's set approximately at 1 to 2 amps. The advantage of performing both cycle-by-cycle RMS recording and waveform inrush recording is you can record voltage RMS, current RMS, active power, reactive power, apparent power, displacement power factor, true power factor, phase angles, active energy, reactive energy, and apparent energy every cycle, as well as getting raw waveform data every time the motor turns on. So if you don't record every cycle, then the data is aggregated over multiple cycles. This is akin to using a low-pass filter, which can lead to false RMS peak values. A single motor inrush test may not tell you the whole story. Depending on the motor load and the motor input, the inrush currents can change. It is best to leave the analyzer recording for extended periods in order to view multiple inrushes. This way, you can be assured that the protection equipment is set properly and the motor is not exceeding its maximum limits. Now let's take a look at a case study. A water reclamation plant was having an issue with a blower motor in a compressor that was intermittently shutting down. They connected the Megger PQ analyzer to the input of the blower motor, and they did a week-long recording. When the recording was completed, they transferred the data to the PC, and they performed an automated data analysis. The data analysis showed that the frequency was drastically out of nominal. Upon seeing this, a frequency chart was created, and it could be seen that the frequency was dropping to 0 Hertz at times. Now, this could be an indicator that perhaps the voltage was actually dropping out. So at this point, we created a voltage trend. It was clear from the voltage trend that the voltage wasn't dropping out. In fact, it was drastically increasing periodically. It was going from a nominal of 290 volts per phase to approximately 430 volts per phase. When these voltage swells were compared to the frequency dips, it was clear that they were related. We then performed a harmonic analysis, and it showed that the predominant harmonic was the zero harmonic. The zero harmonic is DC, and it was 113% of the fundamental voltage. Noting the times each day that the DC was present, the customer was able to identify a piece of equipment that was turning on at that time. A fault in that piece of equipment was placing DC on the input of the blower. So when the DC came on, it would cause the blower to trip offline. Let's take a quick look at the MPQ 1000 and MPQ 2000. The Megger MPQ power quality analyzers are portable PQ analyzers that can be connected to motors while they're online. So there's no interruption to the motor's function. They can record a vast amount of data, and they can record for days, weeks, months, or even years. The power quality parameters the MPQ will record include the following: voltage, current, sags or dips, as well as undervoltages, swells and overvoltages, subcycle waveform distortions, high-speed transients down to 1 microsecond, unbalance, both ANSI and symmetrical components, total harmonic distortion, or THD, total demand distortion, or TDD, harmonics, and interharmonics. The MPQ analyzer will also capture waveforms. Now, these waveforms can be triggered by events. The waveforms can also be triggered by time, and this can be done at the same time, so you can capture both time-triggered periodic waveforms as well as event-triggered waveforms. The MPQ will also trend frequency, active power, reactive power, apparent power, displacement power factor, which is the power factor of the fundamental without the harmonics, as well as true power factor, which is the power factor including the harmonics. The MPQ analyzer will allow you to verify the power supply voltages are correct, as well as balanced. It will record both voltage and current harmonics and interharmonics. High levels of current harmonics as well as high frequencies cause elevated heating in motors that can lead to a host of failures. The MPQ analyzer will analyze harmonics by sequence factor. This allows you to view the negative sequence harmonics that can lead to motor vibrations and additional coil heating. It will record both transients and subcycle distortions that can cause bearing pitting and fluting, as well as insulation breakdown, which will lead to shorted coils. The analyzer will also record all power parameters, as well as power factor. A low power factor can cause motors to be unable to obtain full power. The MPQ can also perform motor startup testing. The analyzer will record all parameters on a cycle-by-cycle basis, and when the motor starts up, it will capture over a minute of inrush current on all channels. And this is every time the motor starts. The unit allows you to perform online motor analysis and motor inrush or startup testing at the same time. During startup, the inrush current can be as high as 13 times the full load rating of the machine. Additionally, the rotor bars are under their highest torque loading, and that can be up to 3 times full load torque during the startup. As a result of this high current draw, voltages can sag. Keep in mind, excessive sags result in longer startup times and additional winding heating and rotor bar stress. Quantifying the voltage sag can identify power supply stiffness issues that, when corrected, can improve system efficiency and prolong motor life. The MPQ 1000 is an 8-channel model which records 4 voltages AC or DC, 4 currents AC or DC. It's a handheld unit powered from an AC outlet or up to 8 hours off a battery. The MPQ 2000 is a 9-channel device that records 4 voltages AC or DC, 5 currents AC or DC, is enclosed in a ruggedized enclosure with isolated inputs, and is powered from phase A or AC or up to 6 hours off a battery. The MPQ analyzers are powerful, simple, portable tools for analyzing power quality and motors. Thank you, and I hope you enjoyed this Megger presentation.